Hi, I'm Aditya, and along with my project partner Kaishavi, we'll be demonstrating the laboratory assignment 7, which is based on a message passing interface for the course EE542. So, MPI is mostly used in supercomputing clusters that have a distributed computer architecture. So, this allows us to create a scalable parallel program using the built-in functions. And MPI also has a built-in support with OS bypassing capabilities for high performance networks. So before I dive into the actual programs that we could run on MPI, I just want to explain what our network looks like. So these are our four hosts that are on the same network, and if you can see, EE0 is different for all the four because these are acting as our elastic interface, and these are all running on AWS, so we need a separate interface so that we could SSH into it. And the ETH one is basically the network that are in the same subnet. So it's in the subnet 10.0.1.0. So it's 11 for host 1, 12 for host 2, 13 for host 3, and 14 for host 4. So that's how I've set it manually. And I've already installed and made all the configuration and the SSH changes needed for MPI so that each host can communicate with the other hosts. And so let's get started with the first program that I'll be showing. So the first one that I'll be showing is the hello world. So before I show the hello world, I just want to show a very simple MPI application that is just to show the host name that the source host can communicate with, right? So for that, just /home /root /host -n. So let's say 6 host name. So let me explain what is happening here, and it's the same for everything. So I'll open the host file on at the other host machine, root/hosts. Right, yeah. So as you can see, for this particular machine, this host file contains the IP address, elastic IP address, I mean the remote instance IP address basically, for all the other instances, right? So 100 signifies host 1, 102 signifies host 3, and 103 signifies host 4. And similarly, for host 1, it's 101, 102, and 103. It doesn't have the IP address for itself. So what this file signifies is that where we need our MPI to be executed. So since I'm running this command on my host 1, and the host file is actually contains the IP address of the hosts of host 2, host 3, and host 4. This will execute on these three machines except in itself. And why am I signifying 6? Because these three machines have 2 CPU cores. So MPI assigns jobs on process based on the cores. So if you see this, so this basically just prints the host name that it could access based on the host machine. So as you can see here, we have 101, 102, 103, and twice of each because we have 2 cores per instance. Just to confirm what our host file has. Yeah, so as you can see on the source host, we have the IP addresses of the host 2, host 3, and host 4. So that's why we don't have anything on host 1. So we'll be keeping the same for all the other programs. So basically what we'll be doing is we'll be running MPI on source host, I mean executing the command of the source host, but the actual program will be executed on the other host. So that's how we're doing parallel program and basically using the cluster. Right, so let's just dive into the first program, that is hello world. Yeah, so I already created my .c file. So before I dive into the code, I just want to compile and run it and show what the output is. And for that I need to compile my code. So the compiler that I'll be using is called MPICC, So just to find where the compiler is installed, I'll do a find command, find /apt. It'll search from there with the name mpeg, just to know where it is. Yeah, so if you can see that the compiler is in this directory. So what I'll do is I'll execute this, just copy and paste this, in fact. Control C, Control V. So this is our compiler. We create an object file, MPI hello world. This is our object executable file that we'll be doing, and we'll do that with the .c, MPI world.c program, right? So this will compile and create an executable, and after we do that, we'll run the MPI on our host, on a remote host, basically, because we are using the host file, the same host file that I showed just a few minutes ago, which has the IP addresses of the host 2, host 3, and host 4, right? So I'll give the full path for the host file. So this will execute based on what I have on my host file. So this will, the MPI will be executed on these machines rather than my source host. So after I do that, it's this -n. Let's use all the processors. So it'll be using all 6 processors of these machines. And what is the program that you're going to run? MPI world. Okay, we need to give the full binary path. So it's an opt/intel/imb/tab/tab source c/MPI world, right? So if we do this, yeah. So you can see we are getting hello world from processor, which has the IP address of 102. 102 means this machine, and we have 6 processors because each machine has 2 cores. So it's based on the increasing rank. So it will first start with this one, rank 0, rank 1, and then rank 2, rank 3, and then rank 4 and rank 5, as you can see, right? So let's dive into what the MPI hello world program is, right? So we first have mpi.h. So we need this just to initialize our MPI environment and do all the necessary MPI tasks. And the first thing is to basically the MPI init. This is just setting up the global variables and internal variables that are constructed, but in our case we are passing it as null. We're not using anything. And then we get the number of processes involved, right, which is done by MPI com size. Now MPI com size takes to basically returns the size of communicator. That's what it does. So we have first the MPI com world. So this returns the amount of processes that were requested for the job, and then we go ahead with MPI com rank. This gives you the rank of the processes. Basically it returns so each process inside a communicator is assigned an incremental rank starting from 0. So that's what I showed in the output, right? So it was rank 0, rank 1 for host 2, and then rank 3, rank 4 for host. So it's an incredible way of assigning the rank, right? And then we get the processor name from MPI max processor name, and that's the function that it uses, MPI get processor name. And MPI finalize basically just terminates all the MPI variables. It's just a cleanup function for the MPI environment. So after this, there are no more MPI calls. So for the printf, as you can see, we get the processor name, world rank, and the world size based on what we are printing. So that's what we are getting: hello world from processor, rank, and what is the size, the processors, the whole processor that we're using, right? So since we passed 6 in our argument, that's what it's printing as the size. So this was hello world. So the next program that I'm going to talk about is the send and receive program. So as you can see, I've already made the .c file and it's everywhere. So you can see the send and receive program. So before I dive into the program, I'll just show you, I'll just run the program just to show what output are we getting. So I copied the compiler's path and I'm creating an executable. So I'm gonna do this everywhere just to keep things coherent. But the thing is, when are you supposed to do this? I mean, where you have to compile? So it's based on what you pass as what you write in your host file. So in my host file, I've written all these 3 hosts, but I'm going to use only just one host for the purpose of the program. So, but just to be on the safe side, I'm going to make the executable on all the machines. Right, so now we have the executable made. Now we're going to do the MPI run command. MPI run. We specify what our host name is, host file is, where our host file is. So it's there. And -n. How many processes do we need? So for this particular program, we just need at least 2. So I'm just going to stick with 2. And I'm going to specify the location of the executable. Oh, okay. So it's not here. It's actually until IMB 294 source C. It's here, right? So when I do that, so as you can see, the process 1 is receiving the number -1 from process 0. So let's just try. Let's just increase our processor. So let's make it to 6. So this means that we're utilizing all our 3 hosts, and it's still 1 and -1. Why is that? Let's dive into the program. Yeah. So first we need MPI.h. So that's why we're using the MPI compiler, and MPI com rank, as I explained in the previous program, that it basically ranks up the processes based on how you have mentioned it in your host file. MPI init, just create the system variables and global variables for MPI. It's null. And MPI com size basically telling you the number of processes present, processes included in this particular task. So this program is assuming at least 2. So why is that? Because the if condition. So if condition is either world rank is 0 or world rank is 1. So it needs only 2 processes just for the sake of this program. So if the world rank is 0, that means if the process is 0, that means if we're using one process of any of the host, then the number is -1 and it'll send this number. So this is the MPI send command function that we're using. So the first is the data that we are sending, the count, that is how much are we sending. Data type is MPI int, that's the data type for MPI variables, and the destination basically tells you about where how much do you need it there, right? So that's destination is 1, tag is 0, and communicator is basically what particular process are we using, right? And in the receive, it's more or less the same. We are getting the data, we are storing it here. The count, that is how much are we getting. The data type that we're using is MPI int, right? Is it a source? No, it's a destination, right? So that's why it's 0. We're giving it a tag 0, and communicator is MPI com world, and status ignore. So we say that process 1 received a number, this thing, from process 0, because we're essentially using only world rank equal to 0 and world rank equals 1, and world rank is nothing but just the process ranks, right? So that's the send and receive .c. Now I'm going to explain a variation of this. We will be using MPI send and MPI receive with it in a different way. So I'm going to explain the next program, that is ping pong. So I've already saved the file on this particular directory, pingpong.c. So before I dive into the code, I just want to run this. So as the name suggests, ping pong is basically one process will send a particular data from one process to other process, depending upon either it's on the same host or a different host, doesn't matter. And you just do that back and forth until you reach a limit. That's the whole idea of this program. So same thing like before, I'm gonna compile this on every host just to be safe. Ping underscore pong dot, that's my executable. I'll just copy this everywhere. Right, so now I'm going to do MPI run. So instead of send receive, I'm going to use ping underscore pong, and I'm going to use two processes because it just needs two. So as you can see, it's a back and forth. So the first number basically signifies the rank of the process. That means the process rank that I just explained. So the process 0 will send and increment the count 1 to 1, and then 1 is the process 1 received that count from the process 0, and then process 1 sends back to the process 0 and increases the ping pong count. So that's how we are keeping track of what is the limit. So as long as we don't hit the limit in our code, the limit is 10. We keep doing this. And let's dive into the code. Before that, let's just experiment how it varies with increasing process. So instead of 2, let's just use 4. Yeah, so this throws an error because we have written in our code that it just needs 2 processes. Let's go right. So same as before, you need MPI.h, and for that you need to use the MPI compiler, and then we create a constant variable which is ping pong limit, that is 10. So this is our limit. We initialize MPI init null again, MPI com rank. We do this to get the rank of the process. We get the total number of processes being used, mcom.size, same as before. So here, as you can see, if the world size is not equal to 2, so that's why it threw an error when we did with 4, because 4 is not equal to 2. So this program runs only with 2 processes. So then we get this error. So world size must be 2 for, and the variable is mcom.world, right? That is the rank. So first we start with the ping pong count equal to 0, and the rank is nothing but what our world rank is plus 1 modulus of 2. Basically it's just choosing the immediate next one. So if our world rank is 0, our partner rank will be 1, and if our world rank is 1, our partner rank will be 0. That's what this means. So because we are only using two processes, right? So that's how we are keeping track of our sender and receiver. So same as before, we are using MPI send. We are sending the number 1 basically, and that's MPI init, and we are sending it to partner rank, and 0 MPI combo, and then that's how we're doing it. So if world equals to ping pong count mod 2, so this signifies that we are process 0 is sending, right? And else signifies that process is receiving, that particular process is receiving if it's odd, right? So we keep doing that, and that's how we are getting ping pong. And MPI finalize, basically it's just a system call, and no MPI stuff is done after this. So that's ping pong. So next I'm going to talk about another variation of sending and receiving using MPI, that is ring. So now I'm going to explain the ring program. I've already made the .c file on all 4 hosts, ring.c, ring.c, right? So I'm going to compile the same way that we did. So instead of this, I have to write ring dot c. Right, and just copy this because the file name is same everywhere. Same as before, I'll first run the program and then dive into the code. So I'm going to use MPI run, and instead of this I'm going to use ring. So just to give you a gist, as the name suggests, ring is basically it starts at process 0. The process 0 will have a token, and then the token is passed to different processes involved in this particular program. So right now I'm using 4, so it will use 4 processes in this cluster, in the cluster of this host, based on what I have in my host file. So host file consists the IP addresses of host 2, host 3 and host 4. So total we have 6 processes because each host has 2 processes, and we are not using the source host as our one of the hosts in the host file, right? So I'm going to do with 4, and let's see what this gives us. So yeah, so as you can see, it starts at process 0. The process 1 receives token -1 from process 0, and then 2 receives from 1, and then 3 receives from 2, and then it ends when 0 receives from the last process. So let's now try with a higher process number. So as you can see, now we are with increased number of processes, the circle is bigger. So it starts with 0, 0 sends to 1, 1 sends to 2, 2 sends to 3, 3 sends to 4, 4 sends to 5, and then 5 sends back to 0. Right? So let's dive into the program. So same as before, we need the mpi.h file, header file, so that the MPI is compiled, and we use MPI com rank. This gives us the rank of the process. This gives us the total number of processes involved, and so we start with so basically, as the command says, that receive from the lower process and send it to a higher process, and we need to take special care for the first process to prevent the deadlock. So if it's not the first process, the other processes will just be receiving first. If it's the first process, it'll just create the token. So the token creation is created, the responsibility is on the process 0, and then the process 0 will send the token around. So that's how we're preventing the deadlock. And if it's a process 0 at the end, it'll also wait for the receive function. If it's not, after just sending, it'll just end its code. So that's how we are avoiding deadlock. And so this is another variation of how to use the MPI send and MPI receive command. Right. So let's look at some other programs for MPI. So the next program that I'm gonna demonstrate is the random walk problem. So the random walk problem is basically that you have a walker, you have a maximum and a minimum, and the walker takes some arbitrary number of steps towards the maximum value, and if it goes out of bounds with the next arbitrary length, then it'll come back. So it'll go warp around and then try again. So that's the random walk problem. So how are we going to use this with parallelization? So if you have a max and a min value, so this is the domain of the size. So if you have a max value, so this is our domain size, and suppose now we have 4 processes, right? So, and min is 0, max is 20. So these 4 processes will be divided into 0 to 4 for process 0, 5 to 9 for process 1, 10 to 14 for process 2, and then 15 to 20. So it's 5 processes for process, 5 steps for processes 0, 1 and 2, and 6 step including the max, because max and min both are inclusive, for the last process, right? So that's how we divide the domain size significantly per process. So if we had only one process, then the domain size will be 20 minus 0 plus 1, so 21 on one process. Instead of that, now we're just using 5 or 6 based on what process you are. right? So the walker starts taking incremental steps, right? So if that step goes beyond the number, so if you have a walker that starts from 0 and it crosses the step 4, then the process 0 has to communicate and send this walker to process 1. So that's how we are basically parallelizing the random walk problem, right? So the process 1 receives the walker and continues walking until it has reached its total walk size of 6, right? So this is just a small step. So what if, because the walker can take arbitrary steps towards the right, what if it takes a huge number? What if it directly takes 20? Then the processes have to communicate with each other to bring that walker to directly 20, right? So I've already compiled the code. So in our case, the random walk is a C++ file, not a C file. So we are using a MPI CXX for compiling C++ codes, and I've done that in all the hosts. Now what I'm going to do is I'm going to first run on one program, right? Yeah, MPI run, already have it created, right? So random walk is what I need, and I'll have to do, so first let me use, instead of 6 I'll use 5 processes, and I'm going to use this. So we are passing arguments for our parameter, so 100, 500 and 20. So let me tell you what these values are. So 100 is basically the domain size, 500 is the maximum walk size, and 20 is the number of walkers per process. So these are our arguments, and let's try to run it. And as you can see, we are getting a lot of stuff in our output. So basically we are printing out for all 20 walkers. So we do this until the processes finish all sending and receiving of all the walkers. So let me just take a quick example. So let's say that process 0 received the walker 18 incoming walkers, and then sends 18 outgoing walkers to process 1, because they took steps more than 1, right? So that's how we're doing it. So since we are using 5 processes and we have 20 per process, we have like 100 walkers in all, right? And I think it's better that I explain the code rather than going over the output. So this just make sure that we have completed all the process, and the process terminates after all the processes finish all sending and receiving of all the walkers, all 100 walkers in overall, right? So let's dive into the code. Yeah. So before I go deeper into the code, I just want to give a brief sort of prerequisite or the characteristics of our code, preliminary characteristics, right? So first, each process determines their part of the domain, and then each process initializes exactly some n number of walkers, and all start at the first value of their local domain, right? Now each walker has two associated integers, the current position of the walker and the number of steps left to take. And then walkers start traversing through the domain and are passed to other processes until they have completed their work. The process terminates when all the workers are finished. Basically, that's what we're going to do, right? So yeah. So first, let me explain what the decomposed domain function is. So the function splits the domain into chunks. Basically, that's why it's called decompose. So based on your rank, that world rank basically gives you the process rank, and it gives you the start and size, subdomain start and subdomain size, and it's just basically divides the overall domain and splits the domain in even chunks, and it also it also takes special care when we have a remainder left, like I showed in this example, right? When we have 21 as a domain size, but we're using only what how many processes are we using? 4 processes we are using. So technically it should be five per yeah, 5 per each process, and then one extra 6 in the last process. So near equal size chunks across process. So this is handled by the function decompose domain. Right. Now we create a function that initializes the walker. Right. So before we do that, we first basically create a data structure, basically a walker structure, and it has 2 variables. One is location and number of steps left in walk. So this is what the prerequisite that I just explained. And then we do the initialization function. So this is all the stuff regarding how we are going to split the domain, right? Decompose domain. And the next function is basically initializing the walkers. So the walker initialization is basically takes the subdomain bounds and adds walkers to an incoming walkers variable. Right. So this is our vector. We're using vector, so that's why we're using C++. So our initialization function, so basically just takes the subdomain bounds and then adds the walkers to an incoming walkers variable vector basically. And after the initialization is done, we do the walk function. So the walk function is basically responsible for progressing the walker until it has finished its walk. So if the walker goes out of its local bounds within the process, then it is added to outgoing walkers vector. So we have 2 vectors, incoming walkers vector and outgoing walkers vector, right? So after the walk function, so we have done the initialization, we have done the walk function. Now what we do is we send the outgoing walkers to the next process. That's why we're using MPI send and send outgoing walkers. And for receiving, we use receive incoming walkers. For that, we use MPI probe because we don't know how many walkers we are receiving, right? So for that, we need to use MPI probe for receiving the incoming walkers. So after we do that, just summarizing what we have done till now. First, we initialize the walkers. We then progress the walkers with the walk function, send out any walkers in the outgoing walkers vector, and then receive new walkers and put them in the incoming walkers vector, and then repeat the steps until all the walkers have been finished, right? So this is where we create our domain size variable, max walk size, and the number of walks per process, and this is what we are getting as arguments from the user, right? And then we do the same thing, MPI init, MPI com size, and then MPI com rank for the process numbers and the process rank. And basically random walk, the name suggests random, right? So that's how we're doing srand to get a random basically random steps. And we create the incoming walkers and outgoing walkers, and it's a vector. We call the decompose. So if we find the part of the domain that we are in right now. So if it's running on a process 2, the domain will automatically be assigned its max and min value of that subdomain. Right? That's how we are outputting, and then we initialize the walkers in our subdomain, and then we basically that's what we are printing, that the process this has initiated with these number of walkers in the subdomain, and the start and the max value. That's how we are giving the range, and then we basically determine the maximum amount of sends and receives needed to complete all the walkers. So we first process all the incoming walkers here within the loop, and then if the world rank is even, then that means that we send all the outgoing walkers to the next process, receive all the incoming walkers. If it's an odd, we first receive and then send, because everything starts with 0, right? That's why. And as same as before, after we are done with all the things related to MPI, we just hit MPI finalize to basically clean and and not to use any more MPI calls, and we return to 0. So that's how the random walk code is written. So the next routines that I'm going to talk about is MPI scatter, MPI gather, and MPI all gather. So let's start with scatter. So broadcast basically sends the same piece of information to all the processes. What scatter does is it sends a chunk of the array to different processes. So let's look at the skeleton for MPI scatter. So MPI scatter has send data and data type, receive data, receive count, receive data type, root, and then MPI communicator. So send data is just an array of data that resides on the root process. The second and third parameters are basically send count and data type, which basically dictate how many elements of a specific MPI data type will be sent to each process. Send count is 1 and send data type is MPI int on our code. And then basically for receiving parameters of the function are nearly identical in respect, and the receive data type buffer it can hold the receive count, and the last parameters root and communicator indicate the root process, and that is scattering the data, and the communicator in which the processes reside. That's what MPI scatter is. Now MPI gather is just the inverse of MPI scatter. So it just collects different chunks of data from different processes and then gathers everything as a whole. It also has a similar structure. And to explain this in more detail, we'll be computing average numbers using MPI scatter and MPI gather. So I've already compiled the .c files and it's already residing on my directory. So let's just run the program. So since I've already created my executable and we need to pass an argument, so I'm passing 100 as my number of elements per process. That's what this number signifies. And let's keep it 5. So we are using 5 processes and 100 per process, so we have 500 numbers. So we need to compute the average of 500 numbers. That's what we are supposed to compute, right? So as you can see, it's close to 0.49. It's going to give us a different answer every time. That is because we are generating random numbers between 0 to 1. But if the number is quite high, the average will always be 0.5. That's the probability rule of normal random variable, right? So if you're choosing random variables from 0 to 1 and your number of elements is quite high, the average is always going to be in the middle of it, 0.5. So let's dive into the code. So just to give you a brief overview of what this program does is basically it generates a random array of numbers on the root process. That is process 0. Process 0 is always a root process. So we have 500 in total. It's 100 per process and we are using 5 processes. So 500 is the array, 500 array numbers, right? We then scatter the numbers to all the processes. So we divide this to all the processes. Then all the processes will perform the average of their own section of numbers, and then the root process then gathers all the averages and it then computes the overall average of these averaged numbers that we get from the sub processes. So let's dive deep into the code. Right. So this is a function to create random numbers. So when we are calling this, this gives us 0 to 1 numbers based on the size, and the number of elements depend upon how much we are passing it as an argument. That is number of elements per process and the number of processes that we are using. right? We then call a function called compute average, just normal simple average computation, right? So we do MPI init, MPI com rank, MPI com size, same thing. And then we create a random array of elements on the root process, and its total size will be the number of elements per process times the number of process. That's what we are doing here. Number of elements per proc is 80 argument of 1, right? So we do create ran in here. If it's a world rank equal to 0, that means if it's a root process. If it's not, we just create a buffer that will hold a subset of the entire array, right? And then we compute the average, and if it's a what we call root process, it will do a scatter and then compute our average, subset average, and we then do a gather from the root process because this is a root process, and then we get the sub averages, and then it performs the overall average. That's how we are getting overall average. And then we clean up, we free, because we're using malloc, we are supposed to free all the dynamically allocated memory blocks. So, and then we do MPI finalize to close everything. So that's our MPI scatter and MPI gather. Now I'm going to talk about another routine which is similar to this, that is MPI all gather. Now scatter is a one-to-many communication pattern and gather is many-to-one communication pattern. So what all gather is nothing but many-to-many communication. So given a set of elements distributed across all processes, MPI all gather will gather all of the elements to all the process. So this is just a figurative description of how MPI all gather works, right? So just like MPI gather, the elements from each process are gathered in the order of their rank, except the elements are gathered to all the processes. That's the only difference, right? MPI all gather structure is almost identical to MPI gather, but the difference that there is no root process. Rest all the same, right? So let's try to run the program. So I'm now used a different program which uses all gather. I'm naming the file as all average. Same purpose. We're just modifying a little bit in our computing average elements, right? So let's do MPI run. Instead of average, we do all average, and let's keep rest the same. If we do that, yeah. So as you can see, the average of all elements is known to all the processes. Since we are using 5 processes, all 5 processes are printing out the overall average, but it's doing the same thing. It's doing the scatter, it's calculating the averages in sub process, and then the overall average is also computed, and MPI all gather is called to print the average of all the elements from each process. Let's dive into the code. So the only difference between average.c and all average.c is that average.c only prints from the root process, and all average prints the overall averages from all of the processes. And of course, average uses MPI gather and all average uses MPI all gather. So rest the same, creating random numbers, that's same, computing the average is same, and we need additional argument just to get the number of elements per process. srand, MPI init, MPI com rank, MPI com size, everything is same. If it's a root process, then when we create the random numbers, we then each process creates a buffer, and MPI scatter will basically scatter the random numbers from root process to all the processes in the MPI world, and then compute the average of our subset. So we get the sub averages. After getting the sub averages, we do all gather, and then we compute the overall average. So each process performs the overall average computation from the sub averages, and we then print from the process. We just print the overall average from each process, and then we do a cleanup. If it's a root process, then we have to clean up the random numbers created because we are using malloc there, and then we free sub averages and free sub random numbers because we're also using malloc there, and then we do MPI finalize. So that's scatter, gather, and all gather. So now we're going to talk about MPI reduce and MPI all reduce subroutines. First, I'll talk about MPI reduce. So for MPI reduce, basically, for example, let's say that we have a list of numbers 1, 2, 3, 4, 5, right? So what if we reduce this list into a single number, right? So if you want to have a sum, then we just do sum and we get 15. If you want to have multiplication, then the multiplication reduction would yield 120 for 1, 2, 3, 4, 5, right? So MPI reduce does this very easily. So this is the skeletal structure for how MPI reduce function is called. So send data is the parameter and array of elements and of the data type, that is data type that we are specifying as MPI underscore data type. And then the received data is basically relevant on the process with a rank of root. That's only it's relevant for. And then the received data array contains the reduced result and has a size of data type into the number of data that is being used. The op parameter is the operation that we wish to perform. So sum, min, max, product. So these are the list of operations that we can perform. And then the root is just to specify whether it's a root process, and MPI com communicator is the same as before. Right, so this is just an illustration of how we can use MPI reduce. So let's suppose we have 3 processes. Each process has a number 5, 2, 7, and 4. And if we want to reduce this to one single number, then we just use MPI sum, and the 0th process, the root process, will get the sum of all the numbers, right? So what happens if we have an array of numbers? So if we have 5, 1, 2, 3, 7, 8, and 4, 2, so we have 4 processes, each have 2 elements. That makes it what, 8 total elements. We can reduce this using MPI sum with 8, 8, and 14. So that's how MPI reduces in a nutshell. So now we'll talk about computing the average of numbers, same way that we did in the last program, but with using MPI reduce. So I've already compiled the .c file, and now we're gonna run the program. Let's do the same way. We have 100 numbers per process, and we're using 5 processes, right? Let's see what this gives us. Yeah, so the local sum for process 2 is this, and the average is 0.493275. Local sum for process 1 is this, the average is 0.48. Local sum for process 3 is this, and this is this. Local sum for process 0 is this. So we get all the numbers within the process, and then we reduce it for using MPI reduce to get the total sum, and then we compute the average. This is the overall average, right? So that's how MPI reduce is being used. Let's dive deeper into the code. Okay. So most of the stuff are fairly similar. We're using create random numbers, same as before, to create a random numbers, and we need 2 variables. That is, we need average number of elements per process, and MPI init, MPI com rank, MPI com size, same as before, srand, same as before. We create random numbers based on how many number of elements per process and how many processes we are using, and then we calculate the local sum using this function. Fairly simple piece of code. And then we print out the local sum based on what process you're running in, and then we use MPI reduce to get the global sum. And after we get the global sum, and if you are a root process, we compute the total sum and the average. Then we do a cleanup, we free the dynamically allocated memory blocks, and then we run MPI finalize. So that's how we use reduce, MPI reduce. So now I'm going to talk about how to use MPI all reduce. Similar to how MPI all gather is to MPI gather, MPI all reduce will also reduce the values and distribute the results to all processes. And similar to the way that how MPI gather differs from MPI all gather, MPI all reduce also doesn't have the need to have a root process ID because the results are distributed to all process. So this is just a figurative description of how MPI all reduce can be used. So 51237842 can be reduced to 1814 8014 8014 8014. So that's how MPI all reduce is used. So now we're going to compute the standard deviation of an array of numbers using MPI all reduce. So I've already compiled the .c file, and I've linked the math library because we're using square root in the code, and this is just a warning that we can ignore. And let's go ahead and try to run the program. Let's do MPI run. So instead of reduce average, we do reduce standard dev, and let's keep everything else the same, right? Yeah. So we get a mean, that is the average, as 0.48979 and the standard deviation as 0.29, right? So let's see what's happening inside the code. So similar to what we have been doing till now, we create random numbers using the number of elements per process, and same thing, we passing that as an argument, MPI init, MPI com rank, MPI com rank, MPI com size, srand, and how we get the random numbers. And now here's the difference. So first we sum the numbers locally, right? That is same. Then we do global sum and we invoke MPI all reduce, and this information global sum is present in all of the processes, not only in the root process, right? So the global sum variable is present in all the processes. We then calculate the mean by dividing the global sum with the number of elements per process that we pass as an argument and the world size. Then we do we basically compute the local sum of the squared differences from the mean. That's how variance is calculated. So the standard deviation is just a square root of the variance, right? So we do local square difference using this, and then we reduce the global sum of the square differences to the root process and print off the answer. So we use MPI reduce here to print out the standard deviation, basically. Sorry, the global square difference, sorry. And then if it's a root process, then we print out the standard deviation. We print out the mean and the standard deviation. And we clean up the rest of the free rands. That's why we're getting only one output, because essentially only root process is printing. We're using all reduce to compute the global sum, right? Everyone knows about the global sum. We get the mean, which is known to everyone. We get the local square differences, and for global square difference we're using MPI reduce here, right? And then we clean up. So that's how we can use MPI reduce and MPI all reduce. So in my demonstration video, I covered the hello world program, I covered the send and receive program, a random walk, scatter, gather, all gather, and reduce and all reduce. The rest of the programs will be covered by my project partner Kaishavi, and that's it from my side of the video demonstration. Thank you.
So till now, we have seen MPI send and MPI receive to perform standard point-to-point communication. Here we will see dynamic receiving with MPI probe and MPI status. MPI supports dynamic messages with few additional function calls. So this is MPI status structure. It includes MPI source, MPI tag, and to find the length of the message, we need to use MPI get count. This is the function MPI get count, MPI status, structure status, data type, and int count. So here is the code. Process 0 is sending a number to process 1. Here we will use MPI status. We'll add one more argument and status to fill this status structure. And after receiving the message, we can check the status to determine the number of received message. So this is MPI get count, and status is the structure of MPI status, and this is the number of count which we received from this message. This is a data type of the message. So we can print it using status.mpi source, status.mpi tag. This is the tag, this is the source of that, and this is a count of the message. And we can use this to probe the number of probe the message size. So for that, we'll use MPI probe to find out the message size before receiving the message. So MPI probe is similar to MPI receive. It does everything except receiving the message. It will block until it receives it finds the matching tag in this function. This function's arguments are the source tag, this is a communicator, and this is the status structure that we just saw. So as we get the message matched to this tag, it will fill the status structure and we will able to get the message size. So here is the code. It's similar to above. The process 0 is sending the message and the process 1 is receiving. So first we are probing it, and as soon as we get the message, the status structure will get filled. And when the probe returns, the status object has the size and other attributes of the incoming message. So here we have used MPI get count to get the message size in it, which will be in the number underscore amount. And then we allocate the memory using malloc of that size of message size. And then we are using MPI receive to receive that message. And as we have allocated memory, we need to free at the last. So this way we can probe the message size and we don't have to allocate more buffer than the message received. So now we'll execute the code of dynamic receiving with MPI probe and MPI status. As we have gone through the code, we can get access to the code of check status and probe on GitHub. So first we will need binary file of this code executable on each of the processors, each of the virtual machines. So I already have executable, which we can see, check status and probe. We'll execute this code using so we'll do MPI run. We need two processes for this because one is the sender, the other one is the receiver, and this is the check status. We are using the check status to check how what is the size of the message we get. So we can see that process 0 has sent 70 numbers to process 1 and process 1 has received 70 numbers from process 0. The source and tag which we have seen, we can see we'll get a similar message. The source, this is the MPI source and this is the MPI tag, which is which is in the structure of status. Here we can see the rank and the tag. Now we will execute MPI probe where we will be probing for message size, and we will get the similar output, and we also need two processes for the same. One is the sender and one is the receiver. So this is its executable file. We'll run this. We can see process 0 sent 21 numbers to 1 and 1 dynamically received 21 numbers from 0. This dynamically is for the probing. We'll first probe the message size and then we'll allocate that memory and then receive the message. So till now we have seen point-to-point communication, but in this section we'll see MPI broadcast and collective communication. So, collective communication is a method of communication which involves participation of all processes in a communicator. So, collective communication implies synchronization point among the processes. So, all processes must reach a point in their code before they can move forward or execute it further. So, MPI gives us a function to implement that, which is MPI barrier. So according to its name, it waits for all the processes to reach a point and then only they can move forward. So here from this diagram, we can see that there are 4 processes 0, 1, 2, 3, and at a time, the process number 0 reached at the barrier, but 1, 2, 3 is still on its way. So we can see that for after some time 1 and 3 also reach to that barrier, and after some time 2 will also reach to that barrier. So after that only it can break the barrier and forward to another execution. So this MPI barrier can be useful in many things. One of the things is to synchronize the program when they are running parallel code. Like if you can't successfully complete an MPI barrier, then you also can't successfully complete any collective call. So if you call MPI barrier in one process, then you must know that every other process is also calling the same function. If it's not the same, it won't work. So broadcasting with MPI broadcast. A broadcast is one of the standard collective communication technique. During a broadcast, one process sends the same data to all of the processes in a communicator, and that one, the uses of broadcasting is to send out user input to a parallel program or send out configuration parameters to all the processes. So here is the diagram, and we can see that the process 0 is sending parameters or any message to all other processes from 1 to 7. So the MPI gives us an MPI broadcast function to do this thing. It has following arguments. The first is the data. The second is the count, size of the data type. The root is the uh, rank of the uh, rank of the process who is broadcasting the message, and the last one is communicator. So we can also do broadcast using MPI send and receive. The one process number 0, here the code is process number 0 will send the message to all other process. We can see that we are using here for loop. The word size is the total number of processes we have. So we are sending the message and the other processes will receive the message, and we are ignoring the status. And so we'll run this code and see what happens. After that, the main problem here is that we are only using one outgoing incoming network link. So this is not very much efficient, and it will take more time. So our process should be in tree-based communication. So as for the diagram, here the process 0 is first sending the message to 1, and at the time when process 0 is sending to process 2, the process 1 is sending the same data to process 3. So these two uh, processes are happening at the same time. These two communication are taking place at the same time, 0 to 2 and 1 to 3. So when we move further, the process 1 is sending a message to 5, 3 is sending to 7, 2 is sending to 6, and 0 is sending to 4. So this, with using tree-based communication algorithm, we can do this very much efficiently and in a less time. So now we will compare the MPI broadcast inbuilt function of a MPI and MPI broadcast written by us using MPI send and MPI receive functions. So here, to compare it, we'll measure the time to broadcast the message. For that, we'll use MPI w_w time function, which takes no arguments, and it simply returns a floating point number of seconds since a set time in the past. It's similar to seize time function. So here we have used a for loop to check how many trials, like we can check for 10 or 5 trials, and then we'll average the time taken for both of those functions and average it. It will give us precise value of time taken to broadcast the message by both of the functions. So first we'll synchronize before starting time using MPI barrier as we have seen before. Then we'll note the time, and we'll use our function, the my broadcast, to broadcast the message. And again, before noting the time, we'll synchronize that all the processes are finished of broadcasting the message using MPI barrier, and then we'll note the time. So difference of this two time will give us the time to send or broadcast the message. So then we'll again synchronize and note the time. Then we'll use the inbuilt MPI broadcast function to broadcast the message to all the processes in this MPI COM word communicator. And before noting the time, we'll again synchronize all those processes using MPI barrier, and the difference between this time will give us time taken for the inbuilt MPI broadcast function to broadcast the message from one process to all other process. So the inbuilt function of MPI broadcast uses the tree-based communication algorithm. So it will give us lesser time than the function written by us using MPI send and MPI receive. So now we'll execute code of MPI broadcast and collective communication. First, let's execute our my broadcast function, which is written by us, like using MPI send and MPI receive. The output will be similar to this. We'll use our two processors of 1 VM. I've already create executables, which can be seen here, compare broadcast and my broadcast. So first, let's run this. We can see this that process 0 is broadcasting data 100 and process 1 received data 100 from root process. The root process is process 0. Now let's compare two functions, my broadcast and inbuilt function given by MPI, which is MPI broadcast. Output will be similar to this. So we are using two processors, and these are the two command line arguments. These are the integers, number of integers, and this is the trials. Since we are using here for loop, how many trials we need to take, and so this one like is integers per broadcast. So we'll get, let's execute this. So we are doing 100 trials, and this is the data size. So we can see that the inbuilt MPI broadcast is giving us less time to execute than the my broadcast, which use MPI send and MPI receive. Now we will move on to performing parallel rank with MPI. So it is useful to get to know about which processor is more faster than another. For that, when processes all have a single number stored in their local memory, it can be useful to know what order the number is in respect to the entire set of numbers contained by all the processes. So, the user might be benchmarking the processes in an MPI cluster and then want to know the order of how fast each processor is relative to others. So, this information can be useful to scheduling tasks. So how we will resolve it, and how we'll get to know that these four processes have what is the ascending or descending series of the processors who are faster than other. So we'll understand parallel rank input and output. Let's understand it using this diagram. So here we have four processes. So now we will see parallel rank with MPI. It can be used for scheduling tasks. So we can get to know that which processor is faster than other. So when processors all have single numbers stored in the local memory, it can be useful to know what order that number is in respect to the entire set of numbers contained by all the processes. So for this we will see the pair rank algorithm. So we know that how to schedule. So we can get to know the rank of each processor in our communicator. We'll see it using a diagram, so it will be easier to understand. Then we'll go to the code. So here there are 4 processors and each has number like 5, 2, 7 and 4. So for our root process, which is 0 here, will gather the numbers and then we need to assign it. We need to remember that process 0 has a number 5 and process 1 has number 2. So we'll attach the ownership information and then we'll sort the numbers using qsort, which is the inbuilt function that we will see later. So here we have sort the number and now we have assigned the ranks by the owner. Okay. And then we'll scatter those ranks. So here we can see that the fastest process is 1. So it is, we have given rank 0 since it has the least number, which is 2. So here the rank will be, the order will be 2, 4, 5 and 7. So it will be 1, 3, 0, 2. So we can see here process 0 has second rank, process 1 has 0, process 2 has 3 and process 3 has 1. So these are the ascending order of the ranks, or we can say that how fast a processor is. So we can use it in scheduling our task with the priority. Now we will see the code. So this is our main function for getting the pair rank. It takes 4 arguments: send data, receive data, data type, and a communicator. The send data will be the output of our parallel rank algorithm, which is the order of ranks, and the receive data will be the number which is taken by all the processors. Now first we'll go create a function gather numbers to the root. So this is a function to take all numbers from different processes of which we need to find order of the rank. So these are the number, data type and communicator. So we are allocating the memory that to this gathered number, so we can use it later after the scope of this function because it is saved in heap. So here we are using MPI gather inbuilt function to gather the data at the root process. And this function will return the gathered number. Now, as I told before, that we need to relate the processor and its number. So we'll define here a structure named com rank number. It includes the rank, and the number can be float or integer. So we have defined it as an union and type def as number. So now we need to get the ranks. So in this function, we'll sort the gathered number and return it to send it to the scatter it to the processes later. So this function returns an array of ordered by processes ranks in its communicator, and this function is only executed on the root process. So its input arguments are gathered number, which is the return value of previous function named gather numbers to root, then the gathered number count, and the data type. Now, as I have told you, we have a structure named comp rank number to attach the ownership. We will allocate it at memory to it. Now we need to assign the ownership to that in that structure. So we have used the for loop and we are copying that. Now, as I told you, we need to sort it in the order. So we'll use the Q sort, which is the already inbuilt. So in that, here we are using if else, because if the input number is float, then we'll use this structure, and if it's integer, otherwise integer, we'll use a different one as it is defined in here, float and integer. Now we have already sorted the order, the ranks, and so now we need it out of the scope of the function. So we'll create one array of ranks and we'll allocate it a memory using malloc. Then we'll copy the data into it, the rank array. So now we have returned the rank array. We need to put all these two functions together in one function that we see in the MPI underscore rank. Gather the numbers, then we'll get the ranks, we'll sort the order of the ranks, and then we need to scatter it to all the processes and then free both of the data structures. So now we will perform parallel rank algorithm on MPI. So here this application simply creates a random number on each process and calls TMPI rank to get the rank of each number. I have already created executable random rank and I'm giving 6 as input processes. So we can see that these are the 6 processes and its rank. Now let's see groups and communicators. So till now we have done point-to-point communication and broadcasting, but if we want to talk to only some of the communicators or some of the processes, what we will do? So we can split or divide our communicators into small communicators and groups. So why do we need that? So we can perform calculation on a subset of the processes in a grid, and if we want to divide the processes and want to process in each row, and each row might want to sum a value. So let's see how we can divide or create sub communicators. So in MPI we have MPI split function which can be used to split our communicator. So the parameters, the arguments are the new, this is our input communicator, the color, key, and this will be our new communicator. So what is color? So it determines like which new communicator each processor will belong. So it will divide the processes in different parts according to communicator. So all the processes which pass in the same value for color are assigned to the same communicator. Okay, and like we can set color as MPI undefined, so with the process won't be included in any of new communicator. So and our third argument is key, which determines the ordering within each new communicator. So the process which passes in the smallest value of the key will be the rank 0, then the next smallest will be the rank 1, and so on. And if the key value conflict of two different processes, the process that had the lower rank in the original communicator will be the first. So let's see it using an example. This is a one communicator. We need to divide it into 4. So we have given each row a different color. So each communicator, subcommunicator now have 4 processes. This is the code of the same. So this is the color. We are dividing it into 4 parts, 4 different colors. Since there are 16 processes, this is the function MPI comp split. Our input communicator, this is the color, the word rank of the each process, and our new communicator. So we have printed down the world rank, world size, row rank, and row size, and then we'll free the new communicator because we don't need it. Now there are also other communicator creation functions like MPI communicator which will duplicate the communicator. I will will think that why do we need the duplicator. So but it is useful for application which use libraries to perform specialized functions such as mathematical libraries. So we don't need any conflict or interference between user codes and library codes. So it is useful there. There is one more function MPI create, in which this is our old communicator, this is a new communicator, this is the group, and then we'll see about there's one other object as it's MPI underscore group. It is also it also does similar work. So in MPI, each communicator has a context or ID, and there's a group of processes in the communicator. So we'll use the ID to distinguish between communicators. So advantages of group, like we can do union or intersection operation on different groups. Like here we can see the union. So now we have the group of 6 processes, and now on intersection we have a group of 2 processes. Other than that, we can compare 2 groups, we can subtract 2 groups, and much more. The good thing about the groups that we can construct a group locally. So there's a difference between a local operation and a remote operation. Like in local operation, we don't need to interact with the other ranks, but in remote operation, we need to decide on the same context and the group. So we can manipulate a group without performing any communication at all. So here's the function of union and intersection, group 1 and group 2. And there's a final new group. Same here. The function to create a new group from a communicator using a distinguish using a tag. So this function takes argument of ranks and the number of the processes in that processes, which will be taken from the given input group, and will create a new group. And the new new group will consist of the ranks inside this array. We'll see this using example. So here is the example. We are getting the world rank and world size of the world communicator. So as I said, this is the array of rank. So this is the rank 1, rank 2, rank 3. The total number of the ranks is 7. So the MPI group will take this number of ranks from the world group and create another group named as prime group. Now we'll create a communicator of this group from the world group and named as prime communicator. Here we will print -1 as rank and -1 as size if the process is not in that communicator, which is our new prime communicator. We are printing all this, and then after all we are freeing the memory because we don't need it anymore. So we'll see its execution of the code. So here we can, I have already created executables, which can see groups and split. This is using the split function, splitting the communicators, and this is the groups. We are creating a group using the rank array. So we can see that we have the group. This is the world rank, which is the 4th, 5th, and 10th rank of total of 16th rank of the processes. And this is the group of 4, total 4 groups, and group of 4, 0, 1, 2, 3. These are the rank and to the size of the group. Now we will execute the group code. As we have seen that in the array we have given 2, 16, 5, 3, 1, 11, 7 rank of processes. So we are getting these processes in our prime communicator. Other one is -1 as written in the code logic. So here our lab 7 is finished. We explore the message passing interface. Thank you.